Okay, I tried to rush through last class, this very end part, and then I realized there's actually stuff in these slides that you need for your midterm. So, I'm going to. This is where we ended, and I'm just gonna continue from here. So we were talking about different kinds of arithmetic, and then we got to pointer arithmetic. So we did like 2's complement, integer arithmetic, and these sorts of things, addition and subtraction, and we got to pointer arithmetic, and then I transitioned into multiplication. Turn this on. And so you have unsigned multiplication where you have two W-bit numbers, and if you multiply two W-bit numbers together, your result is going to have two W-bits, right? 2 times W-bits. And so because you're a W-bit representation, you have to do a mod. So all this multiplication is going to be mod 2 to the W based on your bit width. Just like the addition was mod 2 to the W, same with the multiplication. Okay, so there's nothing too hard to fathom there. The same thing with 2's complement multiplication. Again, use the exact same multiplier. It's just the way you interpret the bits. And so it's not really mod 2 to the W when you get 2's complement multiplication that overflows. You can just get some random stuff back based on the way the bits are set. So you typically want to avoid overflowing your number representation when you're doing multiplication. That means everywhere you're doing a multiply, you have to make sure you're validating the ranges of the operands. So we talked about like the power of 10 rules. It's like you should validate the range of all your inputs before you do that multiply, otherwise you'll get nonsense, which is not good in the program. You'll find that when you're doing multiplication and trying to stay under 4 billion, or actually 2 billion in this case, that's sort of hard. And there's a lot of cases where you want the exact representation. And this is where you have to go with an arbitrary precision math package in order to take, in order to get your numbers with exact precision. And so you'll see this in a bunch of software packages, like, for example, PHP has a big number package. Python's got a big number package. All of these different libraries exist for that. Okay, so you can run into big problems if you don't check for overflow. And this is the security issue from the textbook that they go into. And the issue here is with malloc. And so this particular XDR library did this gathering of data from a data structure. And what it would do, you have this data structure that's pointers to a bunch of data somewhere in memory. And the idea of this library was to consolidate that into one contiguous buffer using a malloc. And then this is the thing that you would send over the network, potentially. So that's the function of this code. This is the implementation. So you see this copy elements. This element source is an array, and this array has pointers, and there's a certain number of counts. So the count is the size of this, and the size is the size of each one of these. And then it wants to do this. So here's the code. And basically, you have this, the array, the count, and the size of each element. And it's doing this malloc, and it does an element count times the element size. And it tries to malloc that. And if it's too big, malloc's going to fail. So if you give it like 2 gigabytes, allocate me 2 gigabytes of memory, it's going to be like, no, I don't want to allocate 2 gigs. That's going to blow up your limit. So like on Linux, there's a fixed limit for the amount of memory any process can allocate. And if you want to allocate 4 gigs, Linux, you have to actually explicitly disable that limit. So if you try to malloc that, this will actually fail. It won't return you the memory. It'll just fail. And this code is doing what it should. It's checking to see if the result is null. Malloc says, "Oh wow, that's way too big." The issue is right here when you do this multiplication, it's not checked for overflow, right? So we saw that multiplication was mod 2 to the W. If you happen to have an element size times an element count that's over 2 to the w. And in this case, this value, element count is an int. Element size is an unsigned int. So not only that, you've got a mixture of unsigned and signed. What happens here is if you manage to allocate more than, if you overflow this integer, so if you try and allocate more than 4 billion bytes, the fact that this multiplication truncates will make it seem like you're actually allocating less. So for example, try selecting an element count and an element size whose product after you multiply them is 2 to the 32 plus 4096. And then because it's modulo 2 to the w, you lop off 2 to the 32, and this allocation actually goes through. Okay, so that's fine. You allocated 4k, but the real damage happens because you pass this check, and then you go and you start copying one element at a time based on the element size. So what do you think that's going to do?
That's going to overflow into everything.
Yeah, that's going to try and write over basically 4 gigs of memory in all sorts of places that it shouldn't, and you'll get a segmentation fault or these sorts of things. All right? So that's where, when the rubber hits the road and you see it in code, that's where these issues show up. Yeah.
Could this also possibly write data that you want to see inside of an area of memory that you might actually have access to?
Yes. Yeah.
Right?
Yeah.
So there's a whole bunch of different security issues that rise up with
Yeah, you have no idea what memory you're writing to, and you'll see in your binaries, in the meta-CTF binaries, as soon as you have an arbitrary write into memory, it's game over. Like, you can hijack the execution of that process. So that's all you need. That's the only foothold you need to take control over a process, is basically what those binaries, hopefully, you'll be able to firsthand experience that problem. Okay, so this is a summary. So here are some values. Element count is 2 to the 20th plus 1. Element size is 4096. Because you didn't validate the input at the beginning of this, like, you could have checked, right? Right at the beginning, you could have checked. And this is what the power of 10 rules say. At the beginning here, just do an assertion. Just try and assert that the product isn't going to overflow by checking the ranges, and then fail out. And that's the idea of that sort of rule of thumb in coding. Because if it's 2 to the 20th plus 1, that's a huge array. And then your size could be, one page. 4K is a typical page size. And then when you multiply these two things together, this is 2 to the 32 plus 2 to the 12, which is 4096. And this is what will blow up the whole thing, basically. So that was an actual vulnerability, and it's talked about in the textbook. And of course, you make it secure by validating the inputs and adding assertions. You could also use the product in the for loop after the check. So if you actually use that here, then maybe it would be okay because it's already truncated. Use the truncated result at the bottom, but depends on how you write your code. Okay. The thing that I need to cover for the exam is multiplication by shifting. And so what happens if you shift a decimal number left one place? Well, here you have 30, and you shift it left one place and add a 0. This multiplies that number by the base, which is 10. So what happens if you shift a binary number left one place? So here you have 00011, and you shift it left by 1, add a 0 from the left, or from the right, sorry. And this turns into 00110. This multiplies the number by the base, 2. So it goes from 3 to 6. So that's easy. What happens if you shift a decimal number left n positions? So here you start with 31. You shift it left 3 positions. You add 3 zeros. This is going to multiply that number by 1,000 or by 10 to the n, where n is 3. Same thing with binary. You shift the number, for example, left by 2 positions. This is going to multiply the number by your base to the n. So 2 to the 2nd power, which is 4. And so you take this 8, shift it to the left by 2, and you get 32. Yeah.
This applies to hex also.
For hex, you take 16 to the n. Yep. Okay. The thing that the compiler often does, it takes a look at your multiplication and says, I can do better than just sending that to the integer multiplier. So the integer multiplier is for arbitrary multiplication. But the compiler knows that there are easier ways of doing multiply than to send it to the integer multiplier. And it often will implement these things using both a combination of shifting and adding. So for example, if you do this number u and you shift it to the left by 3, this is equivalent to u times 8. So this, if you send it to the integer multiplier, is 3 cycles. This is 1. This is a simple barrel shifter. So that's the difference. You can save yourself some cycles. And the compiler, if it knows about your CPU, what target it's compiling to, it knows the cycle counts of each of these operations, and it makes that optimization for you. And it's dependent on the multiplication factor, right? So if it's sort of like a prime number, maybe it's actually going to use the integer multiplier. But if it's a power of 2, well then, yeah, it's just going to use the shift. Yeah.
Would that be done in preprocessor, or would that be done
in the compiling stage?
Yeah.
In the optimization stage. So here are some examples, and this you can practice on that practice site. There's a couple of these on the practice site. So if you have a constant k, you're trying to multiply your number u by 24. You could send that to the integer multiplier, say, mulq $24 with my register. Or what you can do is you can shift that number to the left by 5 positions, and then subtract that the number shifted by 3 positions. So this is actually 32 times the number, is the left shifted by 5, minus 8 times that number, which is 24u. And this turns out to be slightly faster. Doing it on this computation is slightly faster than building this through the multiplier and the adder. Okay. And so for the exam, you're going to be doing this for arbitrary k that are sort of reasonable. So you look for powers of 2, like 18. Well, that's close to 16. So you start with u shifted left by 4. That gets you 16. And then you have to add u shifted left by 1, which is 2 times u, which gets you 18. Okay. The questions about this? All right. So the next part is division by shifting. What happens if you shift a decimal number right 1 digit? Well, you divide the number by the base, but then you round down towards 0. You truncate off this 1 as it goes off the other end. What happens if you shift an unsigned binary number right 1 bit? So here's binary 7, and I shift it right 1 bit, I get binary 3. And so here you divide the number by the base again, 7 divided by 2, and then you also round down towards 0 because this bit gets omitted, that last bit. Okay? Yeah. Because this is an integer value, and so there is no binary point on the end. So when you shift, when you do a shift right, you're removing the bits on the right hand side, and when you do a shift left, the upper bits are dropped off of the representation. Okay?
Sorry, I understand that when you shift it right, you're getting rid of that last one when it has 3 ones.
Mm-hmm.
I'm confused why you round. Which value are you rounding down? What do you mean when you say round down?
So if you actually did this with an arbitrary, so 7 divided by 2 should be 3.5. Okay. But because that binary point isn't being kept, okay, you lop off that half. That if this were a float, then you'd want to keep the half. But because this is integer, you're basically truncating the decimal part after the shift. So that's basically what's happening. Yep. All right. So, question. We just saw that 7 shifted right by 1 position gives you 3. What do you expect negative 7 shifted right by 1 position to give you? Positive large number is one guess. You're going to shift in the sign bit.
Sorry, I forgot about
So you're shifting to the 1, not a 0.
Yeah, for sign. Yeah, we're talking about signed.
I assumed logic or shift, sorry.
4. Negative 4 is one.
Not negative 4, just 4.
Positive 4? Positive 4 is one guess? It'll still be negative, actually. So I'll give you that.
So is it because of that's because it's a...
It's 2's complement.
Yeah.
And so, well, this is assuming this is a signed integer. I should explain that. This is assuming negative 7 is a signed integer.
Oh, right.
And then when you remember we sign extension and we're shifting in the sign for an arithmetic shift right?
It would be 4, yeah.
It would be what?
It would be negative 4.
Okay, one guess for negative 4. Any other guesses?
How many bits do we get?
We have arbitrary number of bits, but yeah, we're shifting it right by one position. And so positive 7 gave you 3. Negative 7 gives you what? Okay, negative 3 and negative 4 are two guesses. I got negative 4. So this is how you calculate that. First you take 7. This is positive 7. And to generate the 2's complement version, the 2's complement of this, the negative 7, you can flip all the bits and add 1. And I'm just doing it for a byte. Assuming this gets stored in a char, this is what you would do. This is your positive 7. This is your representation of negative 7. So it's negative 128 plus 64 plus 32 plus 16 plus 8 plus 1. So you flip the bits and add 1 to get negative 7. And then you right shift it by 1, and it gives you negative 4. Now here is why this is strange, because when you shift a negative sign binary number right 1 bit, you're going to divide the number by the base, but then you're going to round away from 0. Right? It rounds sort of it doesn't round towards 0. So when it's a positive number, you round towards 0, but when it's a negative number, you would be like, why doesn't that round towards 0 too?
It's rounding down.
It's rounding down.
Technically, it's
Yeah.
rounding.
Yeah, but you have to know that. You have to know that, right? Like you're like, well, this is round. They're all rounding sort of the same direction, but you would expect, at least I would expect, this to give you negative 3, because otherwise this, this isn't parallel. I guess is what you're.
So do they both give like 3.5, but because of the round they give you a different?
The truncation, yes.
Okay.
Yeah, because that last bit can't be kept. That's the idea.
I have a small question. So when we convert from this complement, when we flip the bits and we add 1, so we do the entire thing like 1, 1 plus 1 gets 0, and then another 1 is carried over. So we do something like that, or you get the number, you just put 1 at the end.
Well, so if you flip the bits and this was a 0, if this were a 0 to begin with, it'll be a 1 when you flip it, and then you have to add 1 and then do the carry.
Okay.
Yeah, this is intentionally an easy example, just because I didn't want to. Yeah.
I just always get confused with that.
Yeah. So any bit pattern, you flip the bits and add 1, and this one just happened to be easy enough that you don't do a carry when you add 1. Yeah. Yeah, and that was me just trying to give you an easier example. Yeah.
So if you stored that answer in the float.
If you cast that into a float, it depends on where you cast it, whether or not it would get
At the end, when you cast.
at the end of this would give you negative 4.
Okay.
Yeah, and that's an issue. That's a rounding issue that you have to take into account. So these are pictures that summarize this using 15,213. So on this one, you see that this is going to be the floor. This is for unsigned division by shifting. You get the floor because of that. These bits on the right get thrown out. And then for a signed number, for the negative number, this is the round down. And that's just the behavior I wanted to show you. Because rounding does matter. And here are two cases where rounding matters. These are sort of old. But improper rounding caused a change in the parliament makeup in Germany in 1992. So an incorrect round said that rather than having 4.97% of the vote, it actually rounded up to 5 improperly, and then they forced a reorganization of the government on a rounding error. And then the Vancouver Stock Exchange, and this is one of these round down consistently problems. They didn't realize they were always rounding down or truncating rather than doing a proper round. And then the stock index fell from 1,000 to 520 in 22 months. And then when they updated the algorithm to take into account the rounding, that it was truncating instead of rounding. And so the value should have been 1,098. So these are just historical footnotes just to.
This is the case of where, like, if you have eyes of steel, you're fine, right? Because you kept it the whole time.
Yeah. All right. The last example I want to leave you with is operator precedence. So what is the output of this code? So I've done the trick I have I is 3, and I have as a printf on the first one 8 times I minus 2 times I. And then on the second one, I have I shifted left by 3, which is the same as I times 8, minus I shifted left by 1, which is I times 2. What do you think that should be?
Probably
Different. Good call. Yeah, they're different.
Holy crap.
Darn it. So what is going on here? How would you get 6? This is what you would expect, right? This is doing regular PEMDAS. You guys remember PEMDAS? It's doing regular PEMDAS with left to right association. This is not.
It does
That looks
the
like 3 minus I and then shifting to 4 place.
Yeah, something like that. And so what is going on is, I mentioned earlier the operator precedence. And every language has this. And so
Every language has a different.
every language has to follow an operator precedence. They're usually similar, but obviously here are some things that are specific to C, like the arrow, or the pre-increment and the post-increment. Yeah, so some of those are specific to certain languages. But you have to see that, here you go, here's plus and minuses in the middle, and you see that multiplication and division have higher precedence, as you would expect, but the bit shifting has lower. So there you go.
so
This-
when in doubt, parents.
Yeah. So, and in fact, when you do the practice problems, if you do the training problems, that you'll find that, yeah, if you don't put the parentheses in there, in fact, this is sort of why I put this slide in there, because I forgot about this and I got that thing wrong, and I'm like, why is this thing wrong? You know, I had my bit shifting, and then, the fine print. And this is in the standard, so
Is this inherited into C++ too? So if we overload operators?
I believe so. I believe so.
It makes me feel much better. I just parentheses everything. Like,
Oh,
when
yeah.
in doubt,
Yeah, when in doubt. Yeah.
Well,
Put them in
yes,
there. Yeah.
You know,
But yeah, this is a good reference. Like if you are tired of littering your code with parentheses, you could do this. All right. So that is it. So this is the end of the content for the midterm.
Quick question.